Welcome back to ECE 340. Our exam is the next time that we meet. Leading up to that, there have been a few changes. Homework 8 is due today, and I am collecting those. We will talk more about that material today in terms of relationships. So now maybe the lecture will mean more to you today since you've already struggled with it on the homework than what sometimes it might be. Office hours tomorrow, I'm having to change those to be 1 to 3 on tomorrow. If that presents a problem for you, let me know. The Thursday office hours are the typical time from 9 to 11. Our exam is the next time you show up, which is Thursday of this week. We will have a review session tomorrow, and that will be in room 530 upstairs in the ECE building on the 5th floor at 5 p.m. if you're interested in the review session. And I'm tempted to create one big problem and try to work through it in that review session, because we can actually now start connecting all of this material together by presenting you with this big problem, and now you have to analyze the signal, the system, and figure out what the output is. One thing that I should mention as we're going through, our goals for today, before I forget it, is remember what we didn't do in some of the previous exam 2s. You will be responsible this time for block diagram algebra on exam 3. And that may not be on some of the practice exam 3s. Don't forget that. This semester, you will be needing to be able to play with block diagrams. Either take a transfer function, create an all-integrator block diagram, take an all-integrator block diagram, find a state space, etc. That's fair game for exam number 3. And for that reason, the problems might have a little different ratio of what gets emphasized on exam number 3, but Fourier series homework 8 material will be on exam number 3. Today what I want to do is talk about the 3 different Fourier series representations. We finished up, we finished an example of the trigonometric Fourier series. We'll refresh our memory on how we compute those coefficients, the A's and the B's on the trigonometric. Then we will simply show how you can use some trigonometry, or you should know that already. That's why I said let's learn this in chapter B. How do you represent sines and cosines at the same frequency as just a cosine? How do you put those pieces together? That's then going to lead us to the compact trigonometric form, and that one might actually be easier to visualize, because now you just have one amplitude and an angle to think about at each of the harmonics. And the harmonics, if I say second and third harmonic, then you need to know what that means, and that's all going to be dependent on your fundamental frequency. If your fundamental frequency is 6, and I say the second and third harmonic, now we're talking about 12 radians per second and 18 radians per second. And I may or may not ask you for the specific frequency, but typically I'm saying something like, oh, find the power in this output or in this signal between certain frequency intervals. Or I might say, what's the power in the 5th harmonic? And you should be able to then figure out what that is. And the line spectra will actually help us do that. Whether we have the line spectra for the signal that we begin with, sort of the input signal X, or if we have the output signal. And you know how those are connected. These X's, we're breaking those up into sinusoids, and we now know in sinusoidal steady state how to find the output. We just evaluate the system at the given frequency, and that will give us a complex number. That complex number now tells us how the magnitude and angle are influenced in that component of the input at the output. We'll preserve the frequency. It will just now get amplified or attenuated and shifted in time based on how the system shapes that signal. And that shaping of the signal could appear in all sorts of contexts. It could be in signal processing, where you want to filter. Maybe you're trying to attenuate noise. Maybe it's in communication. Now you have ones and zeros you want to communicate across some channel. That may be the airwaves. Now your channel, your H of S, is modeling this channel. And you want to know, how does that channel influence my signal? And I want to capture the information at the other end. And if you know how the signal is distorting or changing your original input, then you can sort of invert that and get the correct information back. Or, so we've talked about signal processing, communication, control. Maybe the input X is some trajectory of a robot arm that you're wanting to maneuver. And the H is the robot arm's dynamics. And you now know, oh, if I command that signal or that robot to move from point A to point B, maybe it kind of rings a little bit before it settles at point B. It might be nice to know that. And all of this is available to you with this information of signals and systems. You can now go into those three different areas. And we'll then talk about the line spectra. Those are usually associated with the last two Fourier series, the compact trigonometric form, magnitude and angle, complex exponential. Now we have a two-sided spectrum, but we still are looking at magnitude and angle. And the magnitude should be even, and the angle will be odd relative to the positive and negative frequencies in your complex exponential form. And all of that is coming to you from Euler. It's really not that much going on. You still have sines and cosines. It's just now you're writing those as these complex exponentials. And that gives you maybe an easier way to think about it or analyze it. And then the power, if I gave you a cosine and said, what's the power in that cosine, that one piece, that one frequency component of a cosine, what would the power be? Or how could you compute the power? If I give you the amplitude, the cosine, omega, I give you omega and I give you the angle theta, what's the average power of that cosine? And that's something we talked about in the very beginning of the semester, but now we're using it now. How do you find the power in a cosine? Amplitude squared divided by 2, right? That's for that particular component. And if you need it for several components, you just find it for each component and add them up. So you might have a watt at this frequency. Maybe you have 25 milliwatts at this other frequency. Now you add them up. But that will provide you with the power in periodic waveforms, and hopefully we'll be able to talk about combining sinusoids, periodicity, and harmonics. But I want you've already done that, I think, for the homework. When is a sum of sinusoids not periodic? So did everybody hear that through the channel? That was the X. The Y didn't come in very well here. But see how this is applicable, the signals and systems? What were we talking about? Oh yes, periodicity of sinusoids. If you had two sinusoids, their sum would be periodic if the ratio of those frequencies is rational. And that allows you to say x of t is equal to x of little t plus capital T, or capital T sub 0. There is some point in time where you could find a repeating pattern. That's really all you're saying, and when those frequencies are rational, pairwise rational, then the sum, the total sum, will be periodic. And the harmonics we've already talked a little bit about. If I said the first harmonic, what's that? That was a vague question, so you can give me a vague answer. You could say omega naught, right? That's the first harmonic. That's n times omega naught, where little n is 1. The second harmonic is 2 omega naught. You have to be told, or you have to find omega naught, and you should be able to find on the exam omega naught. You'll find that indirectly maybe by looking at your graph and saying, where's the first time that this starts repeating? Oh, there's my period, and you can relate period to frequency until you retire, right? Omega is 2 pi f, which is also equal to 2 pi over the period t. This isn't that hard, and I think it's kind of fun. So now you can play in all sorts of areas: signal processing, communication, control, knowing what you know with signals and systems. And we'll go a little bit further. After the exam, we'll move away from Fourier series, which are restricted to what? Periodic waveforms. We want to generalize this, and then we'll get into Fourier transforms. And because now maybe we have some little blip, and we say, what's the frequency content of that blip? And what does that mean? How do we talk about frequency? It's not continuous, it's not going on forever, but maybe this pulse has some frequency associated with it. If I gave you a long blip, and then I gave you a short blip, which would have more higher frequencies associated with it? This blip or that blip? And for those of you just listening, you have to know that I expanded my arms and said the first one was a long wavelength blip, a long blip, and the other one was a short blip in terms of duration. And intuitively, which would you think has the higher frequency content? The shorter one. And we'll figure that out. We'll see its Fourier transform will provide us with this frequency information. And that's just a natural extension of the Fourier series. So if you know the Fourier series stuff, it's natural progression into the Fourier transform. Let's talk quickly. Well, I may just show you. You should know what to expect on exam 3. There's practice exams on D2L. You get one more sheet of notes, so don't get all hung up on your sheets of notes, but make those nice for you. You can use the front and back. Now you have basically 6 pages of notes for exam 3. That's it. And so when I say closed notes, that's with the caveat that you do have 6 pages plus another page that's a copy of the Laplace transform table, table 4.1. You can bring a straight edge if you want. If you want to draw nice horizontal lines for your transfer function, you know, that separate the numerator and the denominator, you can bring a straight edge. I don't know that we'll be doing Bode plots this time. But just in case, if you feel comfortable with that straight edge in your pocket or on your desk, you can bring that. Questions on exam 3. You should be getting comfortable with the process, maybe not the exam, but I want you to start getting comfortable with the material because the final's just around the corner. Questions on exam 3. Let's quickly review what we have learned about the first Fourier series, which is the trigonometric Fourier series. And this one's maybe easier to intuitively think about in terms of computing, finding these A's and B's. The structure of x of t, if we have a periodic waveform, then that periodic waveform is just going to be made up of a sum of sines and cosines, and maybe a DC offset. The average value is that little a sub 0, and that's what this first formula tells us, is that the average value of our periodic waveform, x of t, we will simply represent as a sub 0. Then if I said n equal 5, which harmonic is that? The 5th harmonic. And I could ask you for what's the power in the 5th harmonic. Well, then you would have to find the power in both the cosine and the sine, or maybe you convert it into the compact trigonometric, which is where we're going. To find the other a's and b's, we simply derived this relationship last time. I'm simply going to report it today. Yes? Now the question was, where is the fifth harmonic? So I'm thinking Waldo. Where's Waldo? What you want, if you know omega naught, what's the fifth harmonic? 5 times that. So whatever n plus 1 or n plus 7 floating around, you look at the coefficient that scales cosine of 5 omega naught t. That coefficient will be the amplitude of that fifth harmonic. So don't worry or get too hung up on the n's floating around if they're all over the place. Just find the coefficient associated with the cosine and sine of 5 omega naught t, and that will be your A and B for that fifth harmonic. Does that help answer that question? This is now, and what does this say, this A sub n? This really says x of t, how does it look like, or how does it align, or how is it correlated with cosine of a given frequency, where that frequency is a harmonic of your periodic waveform. If x of t is really nicely correlated or looks very much like cosine of 5 omega naught t, then this A sub n is going to be a big number. If it doesn't look like it, if you basically put x of t, lay it on top of cosine of 5 omega naught t, and when you form that product point for point and then integrate over a period and nothing comes out, then you're basically saying, oh, x of t is orthogonal to cosine of 5 omega naught t, since A sub n was close to 0, or maybe it was 0. It didn't look like cosine of 5 omega naught t, or it didn't have much of that in it. Does that make any sense? That's what these A's and B's are doing. They're basically telling you, what's this x of t, how does it look like these different sines and cosines? And that's what the A's and the B's tell you. They tell you this relationship or correlation with your periodic waveform x of t and the cosine and the sine of the appropriate frequency. You might, in some cases, be able to, whoa, what am I doing? That little n, somebody fell asleep. To be consistent, that should be m, correct? So if you plug that into MATLAB with n there, it would give you something nonsensical if you were looking at b sub n. Did I make any other typos on this? Those are the A's and the B's. And that tells you how your signal, your periodic waveform, is correlated with that set of cosines and that set of sines. And you might end up with A's and B's having little n's or little m's in the denominator. That means your coefficients fall off as the reciprocal of the harmonic. Now, if you have n and m's squared in the denominator, what does that tell you about the A's and the B's? Is this making any sense? You're going to roll off much quicker in your A's and B's, aren't you? They're going to disappear much more rapidly, and so you're going to have much more content at lower frequencies if you have an n squared in the denominator of this coefficient A sub n, or if you had an m squared in the B sub n, versus having those appear as just themselves in the denominator. All right, I'm assuming you're experts at computing the A's and the B's. And now maybe you want to draw a line spectra. You want to say, what's the magnitude at a given harmonic or frequency? Let's now look at the compact trigonometric form, and this is really just converting sines and cosines at the same frequency to a cosine. That's the idea. Let me now write that down. The idea here, and this one's easier to maybe visualize. The idea is to go ahead and convert all of the sinusoids, and when I say sinusoids, that's the generic term. That means sines and cosines. Well, convert all the sinusoids into cosines when we're at the same frequency. Let's sort of go in one direction, and then we'll back out this relationship between the C's and the angle from the A's and the B's. So now we're learning our ABCs. We have our A's and B's, we want to get our C's. Suppose that we want to write this as capital C sub n cosine of n omega naught t plus theta sub n. What you can do now is simply think of this as an angle A and this as an angle B. And now we can simply go back to chapter B at the end, and we have this table of all of these facts, and simply say, oh, the cosine of A plus B, what is that equal to? That's now equal to C sub n times this cosine. And that's cosine A, cosine B, minus sine A, sine B. Plugging those in, we now have cosine of n omega naught t, that's cosine A, cosine B, minus sine of A, which is n omega naught t, sine of B, which is theta sub n, and now we can close up that big bracket. Where this is now again our A, and this is our sort of angle-wise, that's our B in this sum of two angles formula. But theta sub n is just a fixed angle for a given n. If theta sub n is fixed, cosine of theta sub n is just a number. And that's a number that's scaling capital C sub n times this time variation cosine term or piece. So let me just put this cosine of theta sub n together with capital C sub n, and likewise let me combine this sine of theta sub n and this minus with capital C sub n to allow me now to write this. The left-hand side is now equal to C sub n cosine of theta sub n times cosine of n omega naught t minus C sub n sine theta sub n sine of n omega naught t. Just algebra. And this is what you learned maybe in preschool when you were doing the algebra in preschool, or whenever you learn that. Maybe when you're 2 or 3, your mom and dad start talking algebra to you, right? Okay, now we have a word problem. We're going to put in an unknown variable x. Oh, Mom, I know this stuff. All right, so now what do we have? Now we simply can write that as saying, you know what? This looks like what I've already seen. I just had a sum of sines and cosines at the same frequency, and that frequency is a given harmonic. Meaning, now I can rewrite this as little a sub n, that was the coefficient of the cosine piece, plus b sub n sine of n omega naught t. If I now make that connection, or define the little a and the little b relative to the capital C and the angle theta sub n, I can now say that a sub n, little a sub n, is capital C sub n cosine of theta sub n, and that's just a number. And b sub n is minus capital C sub n sine of theta sub n. We can now tell our joke. We want to now relate the c's and the thetas to the a's and the b's, because maybe we've created computationally, we found our a's and b's, and now we have the wrong direction. So we want to now relate this, basically calculate capital C and theta from little a's and little b's. If we take a sub n, square it, and b sub n and square it, now we have capital C sub n squared cosine squared theta sub n plus C sub n squared sine squared of theta sub n. And there is our sine squared and cosine squared adding up if we factor out the C sub n, and we all know that that's equal to 1, right? Sine squared plus cosine squared is equal to 1. This now allows us to express the amplitude in this compact trigonometric form, capital C sub n, in terms of the a's and the b's. That we now know. And we can do something similar to try to find the theta. Now, instead of squaring the a's and the b's, we can take the ratio of those a's and b's, and maybe what we want to do is put that minus sign, maybe multiply by 1 on that right-hand expression for little b sub n, and now we can say that we can find our angle theta. We can now look at C sub n sine of theta sub n over C sub n cosine theta sub n. The C sub n's cancel. Sine over cosine is just the tangent of theta sub n. But in terms of what we've defined little a and little b to be, this numerator on the left-hand side is just minus b sub n, and the denominator is little a sub n. We can now concentrate on the right-hand half of that three-part equality and do the inverse tangent to find theta sub n. We can now say then that theta sub n is equal to the inverse tangent of minus b sub n over a sub n. And now if you're given little a's and little b's, you can now compute the compact trigonometric form. You can now say, oh, the compact trigonometric form of the Fourier series is now going to say x of t is equal to, we'll just call the DC offset capital C sub 0 plus this sum from n equal 1 to infinity, capital C sub n, cosine, here are our harmonics, n omega naught t, plus theta sub n. Where all of these forms of the Fourier series are in the first table of chapter 6 of your textbook on page 599. Questions on the compact trigonometric form and where that and how that arises. But it now gives you a cleaner way, potentially, of thinking about magnitude and angle. And that's consistent with, in a way, the frequency behavior for a system where we were dealing with the Bode plot. That told us how the magnitude varied and the angle varied with continuous frequency. In the Fourier series, let's look at this. We've already actually indirectly computed the compact trigonometric form. in our earlier example, where we were doing the trigonometric Fourier series. What if I now said, here's x of t. Let's say that that's now 1 between t naught over 4 and minus t naught over 4. And then it repeats. From last time, with the amplitude being 1, we found that the average value was 1/2. Little a sub 0 was 1/2. Then the very first coefficient, little a sub 1, I think was 2a over pi. A is 1, capital A is 1, and now we have 2 over pi cosine of t. Oh, I must have now specified what t naught was. What was t naught? Capital T sub 0 is 2 pi. So we're assuming now that t sub 0 is 2 pi. Because we want our first harmonic, our fundamental frequency to be 1 radian per second. And that's equal to 2 pi over t. So t equal to 2 pi gives us 1 radian per second for our first harmonic. And in that x of t, it's even as a function of time, wasn't it? And you can get all hung up on even and odd and what that means, but let me just say for now, when you have an even x of t, your b's are all 0. Meaning in this expression for x, we should only see cosine pieces and no sine terms. And for that reason, it's immediately in the compact trigonometric form because all we have are the cosines. It by default falls out. The second term in this, which is not the second harmonic, it's the third harmonic. The even harmonics were even missing in this expansion, but this is now minus 2 over 3 pi cosine of 3t plus 2 over 5 pi cosine of 5t, and that pattern just keeps going. We have 2 over the odd values of n times pi. So we're skipping the even harmonics. If I said, what's the power in the second harmonic of x of t? That should be a give me. And as I'm collecting your papers, you could say thank you. Right? What's the power in the second harmonic of x of t? There is no second harmonic present, is there? So the power better be 0. You would be looking for a cosine of 2t, and you don't see it. But if I said, what's the power in the third harmonic? Now we're looking at the power associated with this term of cosine of 3t. And how did we say the power is computed? If we simply have sines and cosines, what do? We take their magnitude, we square it, and divide by 2. In this case, we would say, okay, the power, and this is the average power because this is going on and on forever, isn't it? We're not talking about energy. These are power signals now. This is the power in the third harmonic. Now I have to go back and find the amplitude, but that was, technically, it was minus 2 over 3 pi squared, and now we divide it by 2. And this is now 4 over 3 squared pi squared over 2. So I could now say that's 2 over 9 pi squared. And what's pi squared, roughly? Oh, the Engineering 102 students hated this. When I would approximate pi squared as 10. It's basically 10. It's close to 10. It's not calculated. It's pretty close. So, but they really got uncomfortable. They go, I came to school to be precise and accurate, and I'm talking to them in the first semester about making back-of-the-envelope calculations. What? Oh, man. It was a great class. Yes, sir. Oh, I'm sure you want to go 22 over 3 or something. I don't know. What's pi? 22 over 3, roughly? Something like that? I don't know. I talked to my wife, and she starts doing that, and I'm going, oh. But anyway, we have 2 over 9 pi, which is roughly 2 over 90, right? If we're... Humor me. 2 over 90. And now you have an idea. It's 1 over 45, which I would probably say, oh, that's close to 1 over 50, just to give me something to think about, right? So now we have 0.02 watts, 20 milliwatts in the third harmonic of that x of t. Is that making sense? Roughly? Yes, sir. No, if we remember, I'm not sure if I heard that complete question, but the sines and cosines are orthogonal. And so because of that, we're going to be able to take those powers and look at the individual pieces and sum those up individually. So we don't have products of sines and cosines here. We just have a cosine by itself at a given frequency. And because of that, we can now think of the power in each of these harmonics, and if we wanted the total power, we could sum all of these harmonics up, or it might be easier to go and look at x of t and find the power in x of t directly. Yes? There are probably a lot of ways to find the power experimentally in these harmonics, but you could potentially bandpass filter that and say, oh, what's the power in the third harmonic? And now you know what that's doing, right? If we speak of a bandpass filter, but you would then be wanting to, depending on how accurate you want this to be, and the spacing of your frequencies and the sharpness of your bandpass filter, you may say, oh, I have a bandpass filter that's centered at the third harmonic, but if it had a huge passband, you might be including the first, the third, the fifth harmonics in your observational or experimentally obtained answer. So you would need to make sure that your bandpass filter was narrow enough and steep enough in terms of its roll-off into the stop bands. But yes, that's essentially what you're doing. You would be wanting to isolate on specific harmonics by bandpass filtering that x of t. See what you're learning here? Pretty good stuff, huh? What do we want? Oh, yes, we want to go back and now sketch the line spectra for this. Now let's go ahead and I will humor you guys and I will say, let's get the decimal equivalent of this. That's 0.637. So that's pretty fine in terms of resolution. Okay, I didn't approximate too much. Now, what's this? Well, we divide that by 3. So now we have 0.2 something. This ends up being 0.212. Now we need to divide 0.637 by 5, which ends up being 0.13. Now we have actual numerical values for the amplitudes of each of these harmonics. And notice what's happening. We are basically changing the sign at these alternating harmonics, and we're only keeping odd harmonics in this x of t. So there's quite a bit of structure in this x of t Fourier series representation. We want to now visually, pictorially represent this same information. This is the time domain. We want to go into the frequency domain because maybe we want to think about filtering this, either low-pass filtering, band-pass filtering. And what we now get into in terms of looking at this in the frequency domain, now we're interested in the line spectra. And the line spectra is just a way of cataloging or denoting what's happening with the various frequencies. Boom. All right. Have to make this exciting somehow, all right? Here's capital C sub n. C sub 0 was what? Capital C sub 0. And and this is now called the line spectra because these are just going to be lines at unique frequencies. We have a line at the first harmonic. We might have a line at the second harmonic, but we don't have a continuous waveform, do we, of frequencies? We don't have all of the frequencies represented in this x of t because it's a periodic waveform. We only have harmonic content. The DC value is 1/2. That's capital C sub 0. That's what we now write right there. And this is now the DC value. Then we come over here, and at 1 radian per second, which is actually the first harmonic, that was now roughly 2/3, a little less than that, 2 over pi. So that's a little bigger than 1/2. And we can say, oh, here is now the magnitude. So this is the amplitude of capital C sub n. We just want the amplitudes. What happens at the second harmonic? That was actually 0, wasn't it? At the third harmonic, now that's a minus, and if we wanted to, we could maybe show a minus or we could take capital C sub n and go minus, but if we want to show both plots, a magnitude and an angle plot, we'll just look at the absolute value of that. Now we're at 0.212 for that one, relative to 1/2. Let's just say that's right here, and this is now 2 over pi divided by 3, 4, 5, and 5 is now this value that's about 0.13. And we could go on, but you can see that that is decreasing as this odd integer dividing 2 over pi. We start with 0.62 and then we just start chopping it. First by 3, then by 5, then by 7. That's falling off somewhat quickly, but it's not falling off nearly as quickly as if that n was squared. So the tail on this, meaning we have higher frequency content in this signal than if we did if there were squares on those n's in the denominator of those coefficients. Questions on the magnitude. So this is the magnitude. Yes? So the reason I'm doing the absolute value is just so that I can show you that you can also represent the phase. There's 2 pieces to the line spectra. There's a magnitude piece and there's a phase or angle piece. And what I'm doing is I am explicitly saying I want to just create two plots, a magnitude plot and an angle plot. You could collect all of those. In this particular signal, x of t, you can write this as just one plot if you keep track of the sign of capital C sub n, if you allow for negative signs. Then you wouldn't have to show the angle. But what I'm going to do now is I'm going to, instead of writing this as a minus 2 over 3 pi, which was roughly minus 0.212, I'm going to say, oh, that's 0.212 with what kind of an angle? Cosine of 3t with what? Plus pi or minus pi, right? And typically I might say, let's just do minus because that sort of represents a delay relative to a nominal value. Meaning, I could now say this is minus 2 over 3 pi cosine of 3t, or equivalently, I could write this as plus 2 over 3 pi cosine of 3t minus pi. And now I can identify an angle at that third harmonic. Yes? How come it's what? Not negative? Because I'm now just saying, let me, so the question I think was a repeat of the earlier. Why did I concentrate on keeping these positive? Here I'm just trying to show you that you could do it either way. If you wanted to keep track of the angle, in this case, the angle is only plus or minus pi. If it's something that's weird, then you will have to keep track of just the amplitude and the angle. You can't sort of represent an angle of pi over 6 on this magnitude plot. You have to show that with a phase plot. And what I'm wanting to do is now say, in addition to the magnitude, we now have another line spectra, which is the phase, which is theta sub n. And we still have just these angles at the harmonics. There's nothing happening between DC and 1 radian per second. Nothing happening at 1.2 radians per second in frequency content for this little x of t. Is that clear? It's periodic, and all we have to worry about are harmonics. And so now we can just concentrate on lines in the frequency space. That's why these are called line spectra. What was the angle at DC? It was 0, but can you see how you might have an angle at DC? If this was a negative, you could now say, oh, that's 1/2 cosine of pi, or 1/2 cosine of minus pi, and now you might have an angle at DC. Is that clear? Where the cosine of pi is just minus 1. And that would absorb, or that would account for that negative sign. And that's just what? In terms of what's happening, that's just a decrease in the average value of x of t in the time domain, that DC value. The angle at DC, in this example, 0. The angle at the first harmonic, 0, because the sign is positive and there was no angle in the argument of the cosine. The angle of the third harmonic, now we're representing a -1 as cosine of minus pi, or cosine of plus pi. So that now, and how did I do it? I went ahead and said, okay, we have at this particular the third harmonic at 3 radians per second, in this case, we have an angle of minus pi. Does everybody understand where that's coming from? No? So what we're doing is we're saying we had a term that was minus 2 over 3 pi cosine of 3t. That was our third harmonic. What we want to do is we want to write that as 2 over 3 pi cosine of 3t minus pi. And again, we're simply using the fact that the cosine of a plus b, in this case it's cosine of a minus b, is cosine a cosine b plus sine a sine b. Well, the sine of pi is 0, and all we have is then cosine of 3t times cosine of pi, and cosine of pi is minus 1, and that now allows us to make this equality. Does that help? And now we have a magnitude and a phase at the third harmonic. That's why I said let's just keep this as a positive value. Let's just take the magnitude of this coefficient of the third harmonic, and we'll take the sine and absorb it in as an angle. Questions on the line spectra? Now if you have little a's and little b's, you can find the compact trigonometric Fourier series. Once you have the compact trigonometric Fourier series, you better be able to sketch the line spectra. If I give you the line spectra, you better be able to write down little x of t in the time domain. You should be able to go back and forth. Not that hard, but now that you have this, now you know what your filters need to do. If I said just capture the second harmonic, what would you need to do? You could do a bandpass filter that isolates on that frequency at 2. And in this case, you're not going to see anything. You would say, oh, the second harmonic is giving me nothing. And if you did the analysis, you could go, that's exactly what I expected. I'm now filtering x of t, and with the second harmonic, or 2 radians per second, as my bandpass filter, I shouldn't see a thing at the output. Good. That's exactly what I expected. If I now said filter the third harmonic, now you would put in a bandpass filter that was restricted to centered about 3 radians per second, and you would pull off an amplitude of 2 over 3 pi, and you could find the power of that, and we already did. That's that amplitude squared divided by 2. Questions on that? Let's now look at the complex exponential Fourier series. And what was I thinking about when I was saying pi was 22 over 3? It's 22 over 7, isn't it? See, I start thinking about my wife, and I really go crazy. And what? 10 over 3. Well, all right. So that's what got me thinking about 3 in the denominator, was the comment in the back, right? All right, where do we want to go? Complex exponential, Fourier series. This now, what we can do is we can say, here's x of t, here's a sub 0 plus all of these sines and cosines. Let's start with what we know. We're comfortable with little a sub n, cosine of n omega naught t, plus b sub n, sine of n omega naught t. And we are going to sum an infinite number of those terms. But now we want to actually rewrite that as complex exponentials. And now we just are going to use Euler's relationships. We now are going to break this into 2 sums. Both sums are going to go from 1 to infinity. The first sum is going to be associated with the cosine piece. And the cosine in terms of Euler is just e to the j n omega naught t plus e to the minus j n omega naught t all over 2. That's the cosine piece. Then I have the sine piece, plus an infinite sum from 1 to infinity, b sub n, and now this sine is e to the j n omega naught t minus e to the minus j n omega naught t all over 2j. And what I want to do is do a little bit of algebra and come up with an expression for little x of t in terms of e to the j n omega naught t and e to the minus j n omega naught t. Meaning I now have complex phasors that are spinning counterclockwise and clockwise. And those are just sines and cosines. That's what we started with. This is just sines and cosines. But let me now look at what I can do with this second infinite sum. If I now multiply by 1, that's just j over j. Then j squared in the denominator gives me a minus 1. So let me now take that minus 1 and put it up here. And now I have the same denominator in both parenthetical terms. And I can now start looking at collecting the coefficients of the e to the j's and the e to the minus j's. That's what I want to do. Meaning, I can now rewrite this. If I can keep track of what I now have a sub 0 plus a sum from n equal 1 to infinity. And now I want this to be the coefficient or the terms that scale e to the j n omega naught t. If I go up to the first one, I have a 1/2 in common with both, so let me pull that out. And then I have an a sub n in the first one. And I have a minus jb sub n in the second. Is that okay? Here's the minus, that was in red, the j in blue, and the b sub n. And that's scaling e to the j n omega naught t. And that 2 is common to both the a and the b. And what I'm going to do then is actually just say, you know what? That's a complex number. Let me just call that a coefficient, capital X sub n, which can be complex. I'm going to allow capital X sub n to be a complex. That's a weird X, but that little check mark's not supposed to be there. Did everybody see where that came from? Now what I want to do is pull out the piece associated with the e to the minus j. If I go back up, there's still a 1/2 in common with that. And I have an a sub n for the top piece. I have now a 1/2 a sub n, and now I need to go and look at what happens. What's my coefficient that scales e to the minus j n omega naught t? It's just plus j b sub n, isn't it? And this I could actually call x of minus n if I wanted to, meaning now I could, if I had this guy, and x of minus n is really going to be the complex conjugate of capital X sub n. But before I get there, I can now write this, realizing that capital X sub n can represent a complex number. I now have the ability to write little x of t as a sub 0 plus this sum from n equal minus infinity to infinity, meaning now in this summation notation, in the very last one, with sum from little n equal 1 to infinity, x of minus n, I now, if this is going to be capital X sub minus 1, capital X sub minus 2, etc. in this lower summation, and I now have x sub n e to the jn omega naught t. And I do not want n equal to 0 in that form. I've already pulled that out with a sub 0. But if I now say, what about n equals 0? What if I just define that to be capital X sub 0? Then I can pull this little a in, and I can erase that n not equal to 0, and I have a cleaner expression for the complex exponential Fourier series. Meaning now I can write this little x of t as this sum from n equal minus infinity to infinity, capital X sub n e to the j n omega naught t. If we know this is the structure of our complex exponential Fourier series, maybe we don't want to do the little a's and the little b's and try to find the capital Xn's from those. We can find, or we can compute, these complex coefficients, capital X sub n's, by themselves or independently. And how are we going to do that? Now we are asking, really, again, for each of these complex exponentials, e to the j n omega naught t, when you see that, what do I want you to maybe be thinking? If that's confusing, if you say, this seems pretty weird, but what is e to the j n omega naught t? How can you think of that? It's just sines and cosines at a given frequency, isn't it? These are just rotating phasors. Those are just sines and cosines. If somebody now says, oh, e to the j n omega naught t, you can be thinking, oh, that's sines and cosines at n omega naught t. What you want to be able to do now that you have this formula, is address this question: how does one obtain or determine the x sub n's? And how did we find the a's or the b's in the trigonometric Fourier series? What was sort of our strategy for doing that? If I said find a sub 1, how would you find little a sub 1? Yes, so we would scale, we would multiply both sides of our definition by cosine of 1 omega naught t. And then we would integrate all of the terms, and things would start canceling, wouldn't they? Because we would have sines and cosine products. And unless that was a cosine squared, everything would go away, because we would be integrating an integer number of sines and cosines over a fundamental interval of time. The same thing is going to happen here. What we want to do is we want to multiply that definition by this e to the minus j m omega naught t and integrate over one period. Let's do that. So now we're saying here's x of t. We multiply it by e to the minus j m omega naught t dt. and we integrate over one period. So the trick or the strategy here was, if we want something at e to the jn omega naught t, we actually multiply both sides by e to the minus jn omega naught t. And on the right-hand side, this is now equal to this integral over one period t sub 0 of this expansion, this infinite complex exponential expansion, capital X sub n, e to the jn omega naught t, but we now multiplied by e to the minus jm omega naught t, and we want to integrate that. But we can clean that up a little bit, knowing what we know about exponentials. We can combine those exponentials. What we will do now is we will say, okay, we have this difference between n and m. And the only time that that's going to be giving us information is when n is equal to m, or when this becomes 0. When it's non-zero, then we just have an integer multiple of sines and cosines that we're integrating over a period, and those are all going to vanish. Here's the claim. The claim that in all of those infinite pieces on the right-hand side, a lot of those are going to vanish, or all of those will vanish except for one set. All of these are going to be 0 when n and m are different. If m was 5 and n was 4, they're different, and we now have e to the minus j omega naught t. And that's just cosine omega naught t and sine omega naught t. Integrated over one period, we get 0. Here's our validation if you don't believe the claim. So there's our claim ticket, and now we need to go validate our prize, right? Wow. Well, that's okay. You guys are concentrating on figuring out the exam for the next time. Here's our validation. What we want to do now is simply show why that's true. If we now looked at this integral over one period of e to the j n minus m omega naught t. Euler tells us that that's just a combination of cosine and sine. A complex combination, but we now have this integral of cosine n minus m omega naught t dt plus j integral t naught sine n minus m omega naught t dt. And if n is not equal to m, we now have cosine of some integer number omega naught t. And this period t naught is the fundamental associated with omega naught. Meaning we're going to have a large number, but we'll have an integer number of intervals in this period t naught if this difference gets bigger than 1. If we integrate over an integer number of periods, what's the value? We have the same amount of negative area as positive area. This now is gone, as is this integral. The only time we're going to have anything come out that's not 0 is when n is equal to n. Meaning, under this case, we have t naught, x of t. We're multiplying by e to the minus j m omega naught t. That's our left-hand side. But our right-hand side is just going to be 1, and x sub n wasn't a function of frequency. Capital X sub n is now e to the j n minus m omega naught t dt. But we said this, n was equal to m. That now becomes 0. We have e to the j 0. What's this piece? That's 1. And we're integrating over t naught. So this now becomes x sub n t naught. Is that clear? Now we have x sub n or x sub m, since they're equal. We can now solve for x sub n or x sub n, since that's when m is equal to n. Let's just call it m. This is now 1 over t naught, integral over t naught, x of t, e to the minus j m omega naught t dt. And that's how we can find these possibly complex coefficients, capital X sub m, associated with our waveform x of t. And x of t, if we're doing this, we're assuming that x of t is periodic, little x of t. Do we need to do that for another example? Wow. I must have been telling too many stories. I have 100 more pages in 3 minutes. You're going, only 3 more minutes, good. Right? You don't have to answer that one, okay? That one's loaded. Questions on how to find the complex exponential coefficients. If you now find, for our earlier example, where we maybe had something that was like this, maybe that's now a again, let's generalize it, and this is t naught over 4 minus t naught over 4, and then it repeats. If you go through the algebra, you will find that capital X sub n will be a over n pi sine of n pi over 2 for n not equal to 0. And x sub 0 is a over 2, which is what we had for little a sub 0. Now, if these are our x's, can you see that we can sketch the line spectra for this waveform? Now we need to realize that in the complex exponential we have positive frequencies and negative frequencies, and we're going to essentially be scaling things down versus the compact trigonometric, because we have half of it in the positive and half in the negative frequency interval or harmonics. Our line spectra now again could be magnitude and angle, because capital X sub n generically will be a complex number. You will be able to find for that complex number its polar form, its angle and magnitude. And that's then what you sketch as a function of n, where n represents your harmonics. In this case, if we said, what's the magnitude? We would say, okay, here's the magnitude of x sub n, and here is, let's say, omega. In this case, we have a over 2. Then what do we have at little n equal to 1? Sine of pi over 2. That's 1. So now we have a over pi, don't we? So at 1 for n, we now have a over pi. And at minus 1, these are our harmonics, we also have a over pi. But now we have the potential of that being a complex number. In this case, it might be a negative. And so we can now find the phase of x sub n, and we would then have the angle of x sub n at these different frequencies. What's the second harmonic? N is 2 now, isn't it? You plug in 2 in the argument of sine, and you have sine of pi, which is 0. And that's consistent with what we had before. Our second harmonic didn't have any information in it. I'll see you Thursday for the exam, and who knows where we will pick up after the exam. Don't forget, office hours tomorrow have been modified. It's in the afternoon from 1 to 3. Thursday it's 9 to 11, and we have a review session tomorrow night at 5 in room ECE 530.